Alright, and just like last time, we've got our mesh pattern inside of this part. In the previous episode of Nathan Builds Robots, I showed you how you could use screen door material to reinforce your 3D prints. Well, today we're taking it to the next level, and we're going to be using this metal mesh. Now, I bought a bunch of different sizes and thicknesses of metal mesh. I think the sweet spot is going to be this one. This 20 mesh seems pretty ideal. You can see there's quite a bit of room in between these wires to be able to get that interlayer bonding that I need. If you have too many wires there, then there's not going to be enough plastic squishing through and maintaining your interlayer bond strength. And if that happens, you can get delamination relatively easily. These wires are very smooth. It would be much better if I were to acid etch these stainless steel wires, because that would increase the surface area, and then the plastic would adhere to this stuff a lot better. So I might be experimenting with acid in one of my future videos. But for now, I'm just cutting this into strips that I can use to reinforce my print. So I'm just cutting out strips of the correct size, and what I'm going to do here is just use some of these metal cutting scissors. They're called tin snips here in the States, because they used to be used to cut tin roofs. And you want to take really small bites with this thing. You can see I'm not really feeding a ton of mesh into this per squeeze, because these tin snips tend to cut better out towards the tip. So just kind of progress along here, continuing to make small little bites towards the end of the scissors. You get a cleaner shearing action that way, and you get really clean cuts. And you kind of want to guide the scissors to cut right in between two of the parallel wires, because that way you'll just have a much easier time. Now I've got 4 layers of metal mesh. If there's any stray wires like this here, I'm just going to peel those off. The last thing I want is those wires getting loose and causing a short on my hot end. The tricky part about this is that this mesh is about the same thickness as my layer height. If it's not working, I'm going to have to reslice this model using thicker layers where it'll be easier to fit this in between 2 layers. I want everything to be slightly bent down, so I'll take this and just introduce a slight downward curve into the part. So now it wants to kind of arch up like this. Then when I push it down, it should be relatively flat. Then I'll try and hold this in position using some magnets. I'll prime the nozzle a little bit, and now I'm going to try and hold this down while it resumes the print. And if you have any like little spatulas or something, this could help as well. Just because my fingers don't like this 70 or 80 degree heated bed. So if you have little tools that can get in here and lay it flat where it needs to be flat, that will help. And there we go. It looks like it's doing just fine. Alright, let's pull this sucker off the build tray. Oh no. Oh my. This part is too strong and too sticky. Let's clean it up, and we'll start on the second piece. And stuff like this is why I need your help on Patreon. I can't afford to keep buying parts for my printers and all these crazy scientific experiment supplies without your support. The good news is we didn't have any major delamination of, well, other than the delamination of the build surface itself. But this mesh is held in place really well. You can see if I try and peel some of this off, it's actually really stuck in there. I'm sure I could tear this apart if I wanted to, but this just goes to show that it's embedded in there pretty good. And you can see this this mesh is flexible in shear. It can very easily slide back and forth like this. There's going to be a lot of metal little bits to remove here, So let's get to it. Well, this is already a lot more difficult than dealing with glass or carbon fibers. I guess there's less of a risk of airborne hazards in terms of the powder that's generated when you're grinding this down. It's just you've got these little sharp pieces of wire to deal with, which are arguably more annoying. Actually, these little snippers that come with most 3D printers work pretty good at cutting this mesh. Oh, you definitely want to be wearing safety glasses for this though. I find that this kind of rocking action works pretty well. Grab the mesh and then pull and shear away, and it just kind of breaks off these individual wires one at a time, which makes them a lot weaker. I've gotten a lot of this metallic mesh out. It's making a pretty big mess. Now let's go outside and Dremel the rest of this. Ow! Make sure your tetanus boosters are up to date before you start a project like this, because this thing is absolutely perforating my hands. I think it might also be a good idea to get some leather gloves. One last tool I want to try is this deburring tool. It's got a really sharp carbon steel blade, so it should be able to cut through these steel wires. Alright, let's take this outside and see what else we can do here. I did a resonant frequency test on the other two prints, and we're going to do the same thing here, just to get an idea of the relative stiffness to weight ratio of these different parts. Alright, so just like last time, I'm going to take 2 halves of this axe handle and melt them together. I'm thinking that I could just take a wire mesh like this and run some current through it to heat it up, and then squish the other half on top of this. However, when I look at the resistance between the 2 halves of this mesh, it's under 1 ohm. So if I put 24 volts across this, it would be drawing 24 amps, which would be over 500 watts. And I mean, I have power supplies that could probably do it. That would actually be pretty interesting. Then I could just heat this whole mesh up as a single unit, get it glowing hot, and then just smash the 2 halves together. But another interesting way to do this is with this nichrome wire. It's just a resistive element. So I've measured out a length of wire that is about 10 ohms, and I've wrapped it around a piece of filament here. And when I run electricity through this wire, it's going to melt this piece of filament. And this might get interesting if I scrunch this up in between these 2 parts. I can just kind of bend this into shape. So let me just do that real quick. Then when I run current through it, this will all get melted. Then I'm going to come in here with the other half like an Oreo and just kind of smush these 2 together. It'll just kind of be the same plastic that the rest of the thing is made out of, except it's going to be all molten, and it should make it easy to just squish these 2 pieces together. So we'll see how it works. I've got to bend it a little bit more to get it to fit into place here, and there's no better source of heat than the blowtorch. So we'll just kind of melt this and then kind of smush it down, and that should stay in place pretty well. I guess all that's left to do is get the other half of this and heat this up and smush all this stuff together. Well, I only have 1 axe head, and since I need to free it up to try out with the new handle, I guess I'll just break this one. So let's do some destructive testing. We'll hold on to the axe head here and just yank on this and see how much force it takes. Now this is an interesting little feature. The non-reinforced PETG side just shatters and breaks all at once. But when you have fiber reinforcement, it makes the structure a little bit tougher. It's still not that strong, but it's a little bit tougher because those fibers can hold on and keep the structure together for at least a little bit. Let's get the rest of this out of there. And that kind of instantaneous failure that you have in the case of PETG cracking and just failing as if it's made out of glass is not ideal, because if you're swinging this axe head and it just breaks clean off and goes flying somewhere, that's not going to be good for anybody involved. To deliver power to this resistive element, I'm going to be using this power supply. We'll get it turned on and get all ready for the big event. If we deliver the full 30 volts at 5 amps, that's 150 watts. But I'm going to turn the voltage down to 10 just to start out so that we don't have any big surprises here. Now I should already know how much power is going to be delivered through this wire based on some basic information here. I mean, all you need to know is the resistance of a wire and the voltage of your power supply, and that'll tell you how much power is going to be delivered. But just for the sake of practical experimentation, let's attach these wires together. So when we turn this thing on, it's drawing 10 volts at almost 1 amp. That would be 10 watts over this entire length of wire. And that's already starting to heat things up. But if I turn this up to, let's say, 20 volts, that's going to quadruple the amount of power that's being delivered. Or if I turn it all the way up to 30 volts, then again, we're going to be 9 times the power that we were at 10 volts. So yeah, let's just take a quick peek at those numbers. 30 volts at 2.4 amps. You multiply those two together and you get roughly 75 watts. So this is more powerful than a typical 3D printer hot end. The only difference is that that power is spread out over a larger area. So that can just all heat up and melt and get all ooey gooey, and then we squish them together. It'll be just like s'mores. Alright, and just like last time, we've got our mesh pattern inside of this part. You can see that mesh inside of there. And here's our other half of the handle. There's no reinforcement inside of this one. So let's get this heater turned on and melt these two pieces together. And I'm going to use a weight to kind of put some pressure on this. I've got a clamp that I'm going to attach right here, and to kind of spread the load out, I'm going to put the old handle right here. So I'm just going to turn this on and wait for the wire to heat up enough to do its magic. Alright, and I'm increasing the tension over here. Oh my goodness! Alright, so I think we had a short circuit somewhere. When we turn this on, you can see it's dumping a ton of energy into that portion of the wire. So yeah, there's some kind of short circuit in here where it's touching some of the steel wire, and that's preventing the wire from flowing through the path that I was intending for it to go. So yeah, it's that metal reinforcement causing an issue there. It was a neat idea, so I'm going to clean this up and we'll try it one more time. I think all my ideas are sound. I'm just trying too many things at once. Using the metal reinforcement plus this weird conductive heater element thing, all that together ended up in a failure. So we're just running heat through this wire. It's going to get warm, and I'm just going to glue all this down. Alright, and then we'll smack this piece on top and see if this works. Alright, there's a short. This is the issue, is we get that short circuit and then the wires start glowing. Yeah, this isn't gonna work. Time to ventilate. I've spent hours trying to take care of all these tiny little shards of metal that are sticking out, and I've come to the conclusion that it's just way too hard. There's way too many little, slivers of metal. So what I'm going to do is just hit this with enough heat to get this PETG to foam up a little bit, and then that will encapsulate all the ends of these wires and make it safer to handle. It's safe enough for me because I have pretty thick skin, but I want it to be, something that anyone can pick up. So that's a big issue with the type of mesh that I used here. This metal mesh is sharp and it's kind of annoying. Alright, so that pretty much concludes my first video on reinforcing plastic parts with metal meshes. Now, I've got a lot more experimentation to do. There's a ton of things to try out, and as you could see, this thing was pretty good at breaking stuff. I mean, this metal hatchet head provided by Rapidia is pretty sweet, and I'm able to destroy all sorts of stuff with it. Now, I had to keep my experiments brief because I don't really have the time or place to do those kind of experiments unless I, arrange something ahead of time. So if you want to see more experiments where I test this hatchet out, make sure to drop some recommendations in the comments below, and I'll try some of them out. If I need to get some firewood or buy some objects to break, I'll set it up just for you guys. And make sure to like and subscribe to my channel, and consider supporting me on Patreon, because to do these experiments, I've been having to acquire a lot of new gear and tools and equipment. That just really helps cover those costs, and it'll keep these experiments coming. Most of the meshes that I was using were just stainless steel meshes, and it's just a bunch of wires that are woven together. However, I got some of this mesh, which consists of larger wires, and they're actually welded together. They're welded into this great pattern, and I think this will be a lot stronger. Also, the individual wires are much larger, so I can go through and trim each wire individually instead of being in this kind of middle ground where the wires are pretty big, but there's so many of them and they're small enough that it's really difficult for me to properly finish every single wire that's in here. If I was using a grate that was a coarser mesh like this one, then I would have maybe 100 wires tops to cut and trim and make sure they're all good. And I think that would be a lot more manageable. Also, this mesh being welded together is going to provide some added rigidity and strength, so I think it'd be really interesting to try out. Also, I got some of this perforated sheet mesh. That's basically, it starts out as a sheet of aluminum, and then they stamp out a pattern. And if I lay this into a 3D printed part, I think that would embed in there nicely, and it could look pretty cool as well. I've been focusing on getting adequate interlayer bonding by having gaps in between the reinforcing material, so having that plastic seep through and connect with the plastic on the other side, really locking that material in there. But you can approach it in a different way. Instead of using a porous material and relying on the cohesive forces of the plastic on plastic joint, instead, you could focus on really enhancing the adhesion between the plastic and the metal. In that case, you could imagine using a complete layer of just plain old sheet metal with no holes in it, and as long as the plastic is sticking to that sheet metal well enough, then it should be able to just exist in there and reinforce the structure. You run the risk of the whole thing coming delaminated and detached from the sheet metal, and I think that having all these holes in the mesh is more reliable because I really trust the plastic on plastic bond. However, if you were using a material that was prepared in a certain way so that the plastic really stuck to it, I'll be experimenting with some acid. I've got some on the way that I'm going to be, brushing onto these parts just to chemically etch the surface. And that should help me get much better results in terms of the adhesion between the metal and the plastic. In a previous episode, I talked about how when you're using a 3D printing nozzle, you want it to be really slick, as in not sticky. So when you're printing along, the filament won't stick to the nozzle, and that'll help you get cleaner prints. Well, when you're trying to bond a piece of metal into your 3D printed part, you want it to be sticky. So you want the opposite of that slick surface. You want something that's porous and has a lot of surface area and will really stick to that part as good as possible. I guess one issue that you could have if you just had a sheet of sheet metal and you were trying to lay that down on top of your 3D printed part and then kind of embed it into the thing while it's printing, the main issue you're going to have there is that when you lay the sheet of metal down onto the part, that's not going to stick to the half printed part. Like you print up to a certain layer and then you put this on. This won't stick to the previous layer unless you heat it up and drop it on and really melt it in place. But that would be a really risky and challenging operation. You can easily get the plastic to stick to the top of the metal, but getting the metal to stick to the previous layer without doing some sort of heating process is going to be really difficult. But, all of that's doable. It's just, it requires more engineering, more equipment, and more control over the process. What I like about the methods that I've been using so far is that you can pretty much just use a stock 3D printer, get some of this mesh and throw it on there and it works. In terms of the weaknesses of this design, I would say the main issue is all of these little metal wires that are sticking out. I mean, I've done my best to encapsulate all of them, and I would say 90 to 95% of the wires are fully encapsulated, so they don't pose any kind of poking risk. But just one wire here and there sticking out is enough to really ruin your day. It can really cut your hands up or scratch your clothing and and pull the threads apart. So I'm going to have to go through and refinish this. It might make sense to dip it in a layer of epoxy when you're done with it, just to fully encapsulate those wires, because they are pretty dangerous. That's one of the reasons why I kind of want to move to this larger mesh, because there will be less wires and I can go through and take care of them one at a time. But yeah, let me know in the comments what else you want me to test. I've got a real hatchet here and then my 3D printed hatchet, so it might be fun to do a head-to-head comparison of the two. And for these metallic meshes and composites that I'm using, I think it could be really interesting to go deeper into that and do more experimentation. Then there's also the matter of that resistive element that I was using to melt wires into plastic. I think that has some real possibilities for doing some metallic reinforcements. That nichrome wire that I was using actually has a very high tensile strength. It's as strong as high-strength steels. So I think if I just kind of wrap a part in that and then activate it by applying heat and letting it just melt into the part, that could add a ton of extra strength as a post-processing step that could be really easy to do. If you want a lower cost option, you could just use steel or stainless steel wire as well. So there's tons of opportunities for advancement here. And I think that it's something everyone should get involved in. Just be a little bit careful with these meshes, especially the fine ones, because those little wires that stick out can be pretty harmful and hazardous. As you saw, this thing made short work out of that styrofoam. It also was able to smash up this PLA part that I have. This is a quite thick PLA part and I could just smash it up. The edge hasn't really been sharpened. I put a little bit of an edge on there using a Dremel in about 30 seconds, so it's not like properly sharp, but it's a little bit sharper than it was before, and I think that's really helping it cut through cardboard and plastic. Also, I was smacking up that couch's wooden leg and breaking that brick, so this is a pretty strong part. One of the things that I really like about this is that due to that metal reinforcement inside of there, if this whole thing was to just have a crack that just propagated through the entire handle, the head wouldn't go flying because that metal mesh is going to hold things together. So that really adds a level of safety that I think is important if you're doing something like this. When you have a wooden handle, it's designed in such a way that the cracks won't propagate perpendicularly. If you get cracks, they're probably going to run along the length of the handle, and that's not liable to have the whole head of the axe come flying off. Versus if you were just making this out of a solid PETG part, you could imagine a failure mode where the entire head just sheared off and went flying. Having that metal reinforcement really adds that layer of security and safety that I really like. So yeah, I'm not sure where I'm going to go with these experiments. Make sure to support me on Patreon if you want to see more experiments like this, because, you know, it costs anywhere between $100 and $300 just in materials and supplies to make this stuff happen. And I really enjoy doing it. All right, I really would like to talk more about different failure modes and how the adhesion between the matrix material and the reinforcing fibers can fail in various ways. And it just gets into all this composite science that I know a little bit about. But I think in my future episodes, there will be plenty of opportunities to talk about that stuff more. So if you want to follow this series on reinforcing 3D printed parts in situ, then make sure to subscribe to the channel and follow along. As always, thank you guys for watching, and I'll see you in the next episode.